Aha! Are we there? Looks like we're live. All right, that's good. Sorry about that. It was, my fault. Trying to link all this stuff up. The stream is about 20 seconds behind, so I'm actually going to close this window. Are we there? Assuming everything's going to be okay. Actually, I'll bring it up on here instead. That way I can sort of monitor how the stream is going and not be disoriented. Thermochemistry, I want that one. Okay. Can you guys put something in the chat just so I know that's working? Because right now I can't see anything. Well, yeah, I guess send me an email because I can't see anything really in the chat window. I think they're supposed to be. Although I can see it on the live chat, but I don't want to have this open while we're doing our thing. Well, we'll figure that out maybe another time. Although, hang on. Chat's supposed to be there. Yeah, the chat is right there. Well, okay, so here's what we'll have to do. Since for whatever reason, I can't see the chat on the actual YouTube video. Can you guys see what you're typing? I'll have to wait 20 seconds to hear back from you, but if you click on the three dots, it gives you a pop-out chat option. Well, I'm on my iPad. I don't see the three dots. Maybe, hold on. Can I see comments? Is that one? No. No. Well, whatever. We'll just go with it. I'll try and keep this sort of in my view, so we can so I can see what you're saying and sort of respond to it. Okay, so first of all, maybe I'll walk you through what the new assignment sort of procedure is going to be, because that is a little bit different. And we had to do different screens to see chats. Ugh, great. All right, well, I'll figure that out for next time, maybe. We'll see. For now, I do want to go through the new assignment submission procedure. So I will resize this. Okay. Basically, we have to submit everything online now. So, I mean, we don't have to. You don't have to submit it through Brightspace, but it's easier on me if you do. And how we're going to do it, same sort of as usual. You go through content to find the assignment, and down at the bottom you'll see the newest assignment, assignment number 6. Now we haven't gone through that material yet. I'm gonna, briefly summarize it here today, and you can ask any questions that you had either during your reading or during the screencast. And by the way, I hope those are sufficient, like the notes and the screencast. If they're going okay, just let me know and give me a thumbs up or something. If I need to make any modifications, if the quality is not quite right, I can redo some of them, because these were made a couple years ago, and I think the updates could make it easier, although I don't know. I'm not really sure, but hopefully they're sort of sufficing. But the assignment's going to be based off of those notes, essentially, what we would be talking about in class anyway. So when I click on this, it doesn't open a PDF right away. It opens up the assignment Dropbox. Now, the Dropbox is just where you're going to submit your assignment. So here's where the assignment is. Here's where the PDF is. And to submit it, you're going to have an option here. So I'm in the editor. So maybe I'll view this as a student if I could. View as student. Okay, content. Assignment number 6. Again, it doesn't open up the PDF, but it does give an attachment to the PDF. And then once you download it and complete it, I want the same sort of procedure. So like the assignment is going to be the cover page, and you can either print it out and write in manually how much time you spent on it, how difficult it was, and then complete the assignment on separate sheets. Now you can do this electronically if you know how, or you can do it, you can print it out and fill it out sort of manually, like write it out on scratch paper, and just send pictures of that, like put it in a PDF, and then submit that right in here. So you go to upload when you're done the assignment, and then you pick whatever you basically just drop it in there. You don't have to. I think you can just click and drag it. Yeah, you can just drop it right in here, and that'll do it. So I understand that there's maybe going to be some technical difficulties, especially at first. That's totally okay. I'm going to leave the due date. When is the due date? I think it's going to be a week from Wednesday. So we're sort of starting from scratch here. So instead of, I know the first email I sent was a bit premature last week. Hopefully you have looked at some of the material, but we're assuming that last week was just more break, and now we're just going to be basically going from scratch here. So starting this week on Wednesday, that's when the assignment's like released. It's released now, but it's not going to be due until the following Wednesday. So a week from Wednesday. I'll verify that just to make sure. But that was my plan. Assignment 6. Yeah, so let's do April 1st. So that's going to be a week from Wednesday. So if you do have trouble, technical trouble getting any of that stuff figured out, just let me know, and I'll try. I will try to help you out. I actually think I'm pretty good with this. The only part where I'm really technically stupid is the live stream stuff. So I still hate that I can't see the chat in real time. What can you do? Okay, so any questions before we get started? Because my plan for today is just to sort of like breeze over these notes. I mean, I'm not going to go into huge detail, but just sort of summarize it a little bit. I'm kind of counting on you to really get into it and really read into it more. But if there's something that just sort of threw you for a loop, or if I'll sort of point out what stuff is kind of more important or more relevant to the assignment. So yeah, anything before we do that. And I'll wait like 30 seconds because I know the stream is about 20 seconds behind. While we're waiting, I will resize this. Oh, I did figure out a way. I don't know if we're going to need it, but in case we do, in case we ever need it, I'm able to like uh, screen mirror my iPad. So if we ever need to like, if I ever need to write something in real time, I can do it. At least for now, for free. So if that's something that we need, um, we can do that. It's not open right now because the software is kind of, I think, a little bit clunky, but it does show what's on my screen. So there's that. Okay, I'm not seeing any questions, so that I'm taking that as we're good to go. So basically the assignment, I'll bring up the assignment again, just so we know what to focus on here. But the assignment's mostly on entropy and that last bit that we didn't cover before the midterm, the solubility product stuff, more equilibrium stuff. So actually, maybe I should start with that since that's technically the first stuff. And then the thermodynamic stuff. So actually, I think I'll start with that first. Spring, nope. Lectures would be in equilibrium, I think. Solubility product. There we go. Minimize that. Okay, this is going to be the easiest stuff. Well, okay. It's going to be the most familiar stuff because we've talked a lot about the equilibrium constants, and the solubility product is just another equilibrium constant. You know how like when you put some things into water, not all of it dissolves. Some of it dissolves, but not all of it does. And that's because dissolving stuff, like anything, is based off of a sort of a give and take. So some of it dissolves, some of it doesn't, or some of it dissolves and some of it undissolves, right? Some of it precipitates. So that's the equilibrium that's sort of at play here. And so silver chloride is a great example. When you put in some silver chloride into water, it doesn't look like any of it dissolves, but some of it does, just really, really some of it, right? Not a lot of it at all. And so the equilibrium constant for that dissolution is, 2 times 10 to the negative 10, right? So the ratio of products or to reactants is really small, really, really small. And so the solubility product is just going to be the same equilibrium expression as usual, right? Products over reactants. The deal this time is that the reactant is a solid, so it doesn't show up in the equilibrium expression. Okay. So what ends up happening is just the K equilibrium constant is just the product of those two those two products, and that's it. That's it. To their to the power of whatever numbers in front in their balanced chemical equations, but that's essentially it, because solids don't appear in equilibrium expressions. Okay. So basically what they do, they define, so that's the solubility product. The solubility, what people tend to call the solubility, is whatever that concentration is, right? Whatever the concentration of ions in solution is, that's what they refer to as the solubility, right? So if it has a high solubility, then the concentration of ions is high. And if it has a low solubility, then the concentration of ions is low. And that should make some sense, right? Because not necessarily ions, but anything that's dissolved, anything aqueous. And that's sort of how we gauge this. And so if I say, okay, let's let the concentration of Ag plus, just any one of those, equal S or X or whatever, they just use S for solubility. then the KSP, right, the equilibrium constant, is just going to be S times S, right? If silver plus, if I'm calling that S, then chlorine must be the exact same thing, because according to this balanced chemical equation, every time I get one Ag plus, I also get one Cl minus. So they come together, right? So they must be the same thing. So that means KSP is just going to be equal to S times S, right? Since they are equal. And I know what KSP is for silver chloride. It's 2 times 10 to the negative 10. And so S all by itself is going to be, right, the square root of whatever KSP is. So that's the square root of 1.8 times 10 to the negative 10. And so I would call the molar solubility of silver chloride, I'd say it was 1.3 times 10 to the negative 5. That's how that works. And so it's nothing too mysterious, I hope. It is just rehashing the same equilibrium stuff that we were doing before with acids and bases, and just with gases, with stuff in general. But that's sort of how that goes. So I give an example problem here, and the difference here is that it's not a 1-to-1 ratio, but who cares? It's going to be the same procedure, right? And so the question is, okay, given this reaction and its its equilibrium constant, its solubility product, what's the molar solubility? I'm going to follow the same procedure, right? K is going to be equal to this concentration times the concentration of F squared, right? Because there's a 2 right there. And so that's what the equilibrium expression is. I say, okay, whatever the solubility is, it's whatever the concentration of calcium is. I didn't have to do that, but you typically do. You typically choose the one that appears the least amount, though it doesn't really matter. Okay. So I choose that to be my my variable, and then because of that, because it's a 1-to-2 ratio, the concentration of F minus has got to be twice the concentration of calcium, right? That's how that balanced chemical equation reads, 1-to-2. So I just reintroduce, or I substitute those expressions into my equilibrium constant expression. Okay. So when I do that, instead of calcium, it's just S. Instead of F minus, it's 2S. But it's still squared, right? That square doesn't change. It's still there. And so overall, I get 4S cubed. Now, again, I know what KSP is. KSP is 1.46 times 10 to the negative 10 up here. So I know everything in this equation except for S, right? So to find S, to get it all by itself, I just divide both sides by 4 and then take the cube root, which is basically taking that whole expression to the power of 1/3. Okay? And there we go. I think that's, I mean, I'm not going to, wait, am I going to belabor that? Let's see what the assignment looks like. No, I'm not going to belabor that. So typically, whoops. There we go. Sometimes it's more convenient to look at it in terms of like how many grams you can dissolve. So they, instead of the molar solubility, they have like the mass solubility. It's just a conversion. It's not a big deal, but it is maybe more useful in like a lab setting. So you know how many grams you can put in to your solution before it actually becomes saturated, for example. So there are other examples of that sort of here, but it's really the same thing. It's no different here. It's just converting moles to grams. So if you know how to convert moles to grams, then you're in good shape, right? You just multiply by the molar mass. The last piece is the common ion effect. It's, I don't know why it gets its own name, but it's essentially Le Chatelier's principle. because we've already talked about that. So for example, if I have a solution that has like a high chlorine or high chloride concentration, then that'll affect how much AgCl is going to be dissolved, right? Because if any one of these, if the silver ion or the chloride ion, if that concentration goes up, then the equilibrium shifts, right, towards the reactants, which is a solid this time, which means less of this stuff dissolves, right? The equilibrium shifts towards the reactants. It shifts towards the solid, so less solid dissolves, okay? That's sort of how that goes. So you can affect how soluble something is. So if it's like too soluble for whatever reason, and you really don't want any silver in your solution, like hardly any, like let's say the what do we have before? 1.3 times 10 to the negative 5 molar. Let's say that is too concentrated. Like it's beyond the threshold that we can allow for silver. We don't want it to be that high. Pretend it's not silver. Pretend it's I don't know, cyanide or something. So, something you don't want in your water. So in order to do that, in order to lower that concentration, we can. All we have to do is take chloride. If this is the source of AgCl, is the source of silver, then we just up the chloride concentration in our water, and then less silver chloride is going to precipitate, or is going to dissolve, which means less silver ion in our solution. Okay, that's the idea. So just by trying to dissolve this in a 0.05 molar NaCl solution, that Cl minus is no longer S, right? It's now 0.05. Right? That's way bigger than whatever S was, right? S was like 1.3 times 10 to the negative 5. So this is definitely a lot bigger than it. So the chloride ion concentration is just 0.05. Ag plus is still going to be S, and that is still the equilibrium constant for the dissolution of AgCl. And so the solubility, right, the concentration of Ag plus went way down because of that. So that's essentially how you can sort of taper how much ion you want in your solution, because sometimes you don't want a lot of a particular ion in there, and you can it's basically just using Le Chatelier to force it to not go. All right. Any questions on that before I go just talking about thermochem? Again, it's just going to be me sort of doing nothing for a little bit, just because it lags by 20 seconds. So at any point, if I see anything in the chat, I'll address it right then and there. And I hope it is addressing it there. Yeah, we're good. Okay. So the first part of thermo it's kind of a review. So, if I have gas on this side and I open this valve to sort of let it spread out, that's what it's going to do. There's zero pressure on this side, so there's zero resistance to it, and the gas just expands to fill the whole container. The problem with that, is that according to the first law of thermodynamics, absolutely nothing happened, but clearly something did. And the reason why I say nothing happened is because, well, the temperature didn't change, so there's no change in internal energy. The molecules still have the same energy that they had, they just have more space. There was no work done because, well, there was no resistance. So you didn't have to push against anything. So there's zero resistance on the other side. So there's no work done to do that expansion. And so if there was no change in internal energy, if there was no work done, that must mean Q is equal to 0 as well. So the first law of thermodynamics has absolutely nothing to say about what just happened here. But something definitely happened there. So that's the rationale behind introducing a new variable, something that matters sort of just as much. And it's kind of true in another sense where, and we'll see this later in the term, unfortunately you won't be able, actually you actually could build your own battery if you wanted to, but essentially the power that's stored in that battery, the energy available, the total energy, is not the same as the energy available to you. So it might be like a 3-volt battery, but you might only be getting 2.5 volts out of it, and that's the best you can do, right? So the amount of energy that's actually available to you isn't quite the maximum amount, okay? Because some of it has to be dissipated to heat. That's the idea. That's or not necessarily heat, but I mean it is heat, but it's more like chaos. It's being converted into chaos essentially. Okay. So this is just a recap of the first law. Change in internal energy is the heat energy plus the work. That's what we've been going with so far. In that scenario, no work was done. There's no heat transferred, so there's no change in internal energy. So we look at the second law. So remember the first law was that energy can neither be created or destroyed. You can only break even. Okay, but the second law is a caveat to that. It says, well, you can't even break even. Okay, no matter how much energy that you think you got, some of it's going to be sort of sacrificed. Okay, and so the entropy, this new sort of term that we're introducing here, is going to increase. That, like, naturally, left to its own devices, the universe tends to want to become more chaotic, not less, right? You leave your room, you don't clean your room, then it gets messy, right? That's just how it goes, right? It doesn't clean itself. You have to actually do work to unmess it up. Okay, so as for why the particles did spread out, because again, it has nothing to do with the first law. It has everything to do with statistics. Okay, just statistically speaking, it is much more likely that the gas is going to spread out because there are many more states that it can occupy in that sort of orientation. And the deal here is a picture sort of one of these at a time. So if I only got one atom, and those are the two sort of regions, the two flasks that it could be in, well, it's either in one or the other. If there's only one atom, it's either here or it's here, right? So those are two possibilities, two possible states that are equally likely, right? Now, if there are two atoms, well, I can split them. I can have both of them on this side, or I could have both of them on that side, or I could have one over here and one over here, or I could swap them, right? So there are two states where there's one in each of them, right? But that's a total of 4 states, right? One where they're both on the left side, one where they're both on the right side, and 2 where they're split evenly, right? There's one over here and one over here. And you just keep doing that. You keep doing that sort of analysis until you get to like more than 2 atoms. If you get to like a mole worth of atoms, there are many possible states. There are 2 to the power of 6.022 times 10 to the 23 possible states, right? That's a lot of possibilities. So the question becomes, with that many states, what is the probability? What are the chances that every single one of those 6.022 times 10 to the 23 atoms are on one side? What are the chances of that? Well, it's going to be 2, right? Because they're either on this side or they're all on this side. So that's 2 of them. 2 out of that number. So 2 divided by 2 to the power of Na. So that's very small. There's no chance. There's no chance that's happening. So it really is just a probability thing. So that probability, again, for them to all be on the left side, there's only one state where that's true. So it's 1 over 2 to the power of Na, which is essentially 0. Okay. Now, I don't know how the online text describes entropy, but I like to think of it as molecular freedom. So it's essentially how much elbow room it's got, essentially. If it's being held down at all, if it's being, if there's any barrier to its moving around, then it's got less entropy, essentially. So gases have all kinds of molecular freedom, so their entropies tend to be quite high. Liquids are they're closer to each other, they don't have as much elbow room, so their entropy is lower than gases. And solids don't have much movement at all, especially if they're in like a crystal. They got nothing. I'm actually not going to focus on the math so much here because not super relevant. But the concept is relevant. Okay, so get comfortable with this extra added feature where we now care about how much freedom these molecules have. Okay. You can describe it mathematically. I'm not going to focus on this part. This is more like physical. This is more physics to be honest. So I'm going to skip a lot of that. If you are interested in any of this, again, go through it. But I reserve this stuff mostly for like a physics class. So anyone who's taken physics with me, you probably, and we did thermo, you'll probably recognize a lot of this. The last laws of thermodynamics. So we went through the first one, the second one. Remember the second law is that you can't break even. I mean, unless the temperature is 0. So if the temperature is 0, just sort of mathematically speaking, just by these equations, if the temperature is 0, then you could actually break even. But the third law says that you can't get to absolute 0. So no, you can't. You cannot break even. So, and the rationale there is because at absolute 0, the entropy must be 0, because if you're 0 temperature, then you've got no energy to move. Okay, but you can't do that because there's always going to be a transfer of energy from one hot body to a cold body. So you can never actually get to absolute 0. That's how the 0th law is sort of summarized here. All right. Now, how to use this to sort of make meaningful predictions? If we're looking at phase changes, where a solid's going to a liquid, to a gas, or the other way around, these processes take energy, and they're definitely a change in entropy. Okay, so in order for a solid to melt to a liquid, well, I've got to invest energy into it, so that means delta H is greater than 0. But also, from a solid to a liquid, the amount of molecular freedom it got, the amount of movement that it got, increased, right? So the entropy went up as well. So as I'm going from left to right here, both quantities are increasing. The amount of energy that I need to input and the amount of molecular freedom these things get, right? And it's the exact opposite going the other way. So to condense a gas to a liquid, I need to remove heat energy from it. So that's negative enthalpy. But it's also losing some molecular freedom because I'm sort of locking it into a liquid state where they have to interact with each other now. So the entropy goes down as well. And to see whether or not this is spontaneous, I just have to check if the entropy of the universe is greater than 0. That's the condition. So maybe if you could, I don't know if you have this printed out or whatever, but this part right here is kind of important. This is like this is the highlighted option here. So maybe I'll just highlight it. There. If that condition is true, then it's spontaneous. Because remember, the universe wants to spontaneously, or sort of all on its own, gets more chaotic. So that's the condition for our reactions. At absolute 0, entropy must be 0. Then you said it can never actually get to 0. Can you explain that? Yeah, that's the third law. So the third law is if we can get to absolute 0, then the entropy's got to be 0 because there's no movement, right? Picture yourself at absolute 0. Like if it's really cold outside, you're not really moving. You're just frozen. That's sort of what the molecules are going to do. Okay, at absolute 0. That's the third law. The 0th law. It's the 0th because they discovered it sort of too late, or they thought about it too late. But the 0th law is that condition, like getting to absolute 0, is impossible. That's all. So the 0th law sort of says, no, you can't get to absolute 0. And the third law is just saying if we could get to absolute 0, then the entropy would be 0. But the 0th law says you can't get to absolute 0. So there's no way around it. That's the combination of those laws. First, second, third, and 0th. You just can't you can't break even. If you invest like $5, you're not going to get $5 back out. You're not going to be able to spend $5. You're going to get less than that. Someone's always going to take a cut, right? And the person who's taking a cut is Mr. Entropy. So here we go. I'm just going to check if this condition is true. Now, the entropy of the universe is going to be the entropy of the system and the entropy of the surroundings. So the entropy of the system, I'm going to leave that alone. But the entropy of the surroundings, I'm just, right here, I'm inputting one of the equations that I have above. It's sort of like an isothermal cheat code. Because, I mean, in reality, when I have like a little beaker here with a phase change, the temperature of the rest of the universe isn't changing that much. So that's why I sort of put this expression in there, because temperature of the surroundings really is not going to change. The surroundings is literally the rest of the universe. So I just make that substitution, and then I can sort of factor out the entropy of the system here. And so what we get is, and this is the key part here, the entropy of the universe, which is what I'm using to test whether or not something is spontaneous, that is going to equal the entropy of the system. And it's also going to depend on the ratio of these temperatures, the temperature of the system versus the temperature of the surroundings. Now, it's displayed mathematically, but I bet it makes sense to you if I put it this way. Does ice melt spontaneously? Sometimes, if the temperature's high enough, right? It doesn't melt spontaneously if the temperature's below 0, right? So whether or not this is a spontaneous process, melting ice, depends on the temperature of the outdoors and the temperature of the system itself, right? So if the temperature of the surroundings isn't high enough, then no, it's not going to be positive, right? Picture if the temperature of the surroundings is bigger than the temperature of the temperature of the surroundings is actually smaller than the temperature of the system, then this whole fraction becomes bigger than 1. And 1 minus something bigger than 1 is a negative number. So if it's a negative number here, then the change in entropy of the universe is also negative, which means it's not spontaneous. Okay. So that's why I focused on that fraction. If the temperature, if that ratio is less than 1, then it could be spontaneous, so long as the entropy of the system is also positive, or vice versa, because that happens too. The entropy of the system in our case could be a reaction. So an example where the entropy of the system is greater than 0 would be like a dissolving, right? That's a good one, because it was one thing and then it split out into 2 or more things. So that's an example of a spontaneous sort of process. And the opposite would be true for a negative entropy system. That's where, like, a combination reaction, where 2 things were by themselves, but then they came together, right? So that would be a lower entropy than before. So I just harp on that just because the equation says it depends on what kind of reaction you're talking about, whether you want a high temperature or a low temperature. That's all that means. Or in our case, the changing phases, if it's a positive entropy, so if I'm going from solid to liquid, if I'm melting it, then I absolutely want the temperature of the surroundings to be higher, because I want it to spontaneously melt. But if I'm going the other way, if I'm going from liquid to solid, well, the entropy is negative there, right? And it's not going to freeze spontaneously unless the temperature is really low, right? That's the idea. So that's why there's a difference between these two. For vaporization, typically, it's kind of they're not all 88, but it tends to be what they are. And the reason we look at the entropy of vaporization and we assign it like a sort of a constant value is because, remember, in the gas state there are 0 intermolecular forces, essentially, right? So because there's no interaction with the molecules, they have essentially not infinite freedom, but the most freedom that they're ever going to have. Okay, so because that's the same case for any gas, we can sort of assign a relatively stable entropy change for that process for vaporization, and it's usually around 88 joules per Kelvin mole. Okay, higher for water, because water has hydrogen bonds in it. Okay, so in the liquid state, it's actually got a lot more rigidity. It's got less molecular freedom in the liquid state. So the change in entropy when it gets to the gas state is actually higher, because not only it's actually more constrained than most liquids. Okay, that's why it's a bit higher for water. Okay. So I give an example here. Is boiling water a spontaneous process? Depends. If the entropy of the universe is greater than 0, then yeah. So let's see. I'm just going to use the entropy of the vaporization. So that's boiling, right? So that entropy for water is 108.9 joules per Kelvin mole. And then plus the entropy of the surroundings. Well, if the system's getting energy from the surroundings, then the surroundings lost energy, right? So that's why there's a little negative sign there, because that 108.9 didn't come from nowhere. It came from the surroundings, right? So they lost energy. And so I put negative Q over T, again, using the same sort of trick that I used above. But Q is just the heat energy, which is just the enthalpy of vaporization, right? Because we're doing this over the benchtop. There are some technical reasons why this works, but you'll just have to trust me for now. It works. And that's a number that I know. That's a number we could have figured out last term, right? This to find the enthalpy of vaporization. Well, one, you could just look it up, or two, you just take the enthalpy of the products minus the enthalpy of the reactants, and you'll get 40,680 essentially. Okay. So with that, is it a spontaneous process? Well, it depends what the temperature of the surroundings are, right? If the temperature of the surroundings is sort of too small, so if the temperature of the surroundings is really, really small, this whole fraction becomes really, really big, right? And so I get, if this number ends up being bigger than 108.9, then this subtraction is going to end up being a negative number, because I'm going to have 108.9 minus something bigger than 108.9, and that's going to leave me with a negative number. And negative number means not spontaneous. Okay. But on the other hand, if this fraction is really small, or if it's smaller than 108.9, then I'll end up with something positive for delta S of the universe. And this can only be really small if the temperature of the surroundings is big enough. See how that works? And it's something you would have known sort of intuitively anyway. Does boiling happen spontaneously? If it's hot enough, then yeah, right? So it turns out when you take the ratio of those numbers, so when you rearrange them, so the threshold, right? If it's greater than 0, then it's spontaneous. If it's less than 0, it's non-spontaneous. So right smack in the middle is 0. So all I did here is I took that entropy of the universe, I set it equal to 0, and then I rearranged for T surroundings. That's all that happened there. So rearranging for T surroundings with delta S of the universe being 0, being at that threshold of being spontaneous or not, that ended up equaling just the enthalpy over the entropy. So 40,680 joules per mole divided by 108.9 joules per Kelvin mole, and that left me with 373 Kelvin. So that's the threshold temperature at which it becomes spontaneous, which is what the boiling point of water is, right? Water boils at 100 degrees Celsius or 373 Kelvin, right? So long as the temperature of the surroundings is bigger than that, then it's going to boil spontaneously. If it's lower than that, it's not going to boil spontaneously. Okay? That's how that works. Questions there? And this is just the general sort of equation for it. In general, if you want that threshold temperature, it's going to be the enthalpy over the entropy. Now, whether or not it's got to be bigger than that or smaller than that depends on whether the entropy is positive or negative for this process or this reaction. So that's something you'll have to sort of like intuitively gauge. All right, give me a gauge on how we're doing sort of energy-wise. Because I plan to stop probably in like 5 minutes. Or stop lecturing anyway in like 5 minutes. Because we're already like halfway through the thermo stuff. And then we'll talk more logistics. Same stuff is happening with reactions. So I'll just cover reactions, like whether a reaction is spontaneous or not, using entropy, again, the entropy of the universe. I'll apply it to reactions and not just processes. Okay. So luckily, to find the entropy of a reaction is really easy. It's really familiar. You're just going to do the same thing you would have done to find the enthalpy of the reaction. You're going to look up a data table, and I just go on Google and I look up entropy table or like standard entropy table, and those are the numbers that I use. I think your book probably has an appendix with thermodynamic data, entropy is going to be one of those entries. Okay? But essentially, it's the same thing. Products, the sum of all the entropies of the products, minus the sum of all the entropies for the reactants, multiplied by their stoichiometric numbers. So everyone remember doing that? It's the same process that you did for enthalpies. Products minus reactants, multiplied by whatever number is in front of them in the balanced chemical equation. So in this case, in this particular reaction, I've got barium hydroxide plus 2 ammonium chlorides going to barium chloride plus ammonia plus 2 ammonias and plus 2 waters. Now the states really do matter because the entropy for barium chloride in the solid state is different than the entropy for barium chloride in the liquid state or the aqueous state or the gas state. So you do have to make sure that you're looking at the right entropy number in that table, because there are going to be different numbers for each of these in their different phases. Okay, so the states really do matter. I look up the delta S of the reaction. I look up the entropy for barium chloride in the solid state, right, the first product, plus 2 times, because there's a 2 there, 2 times the entropy for ammonia in the gas state, plus 2 times the entropy for water in the liquid state. Okay, so that's all of that. That's all like the right side, the product side of the reaction. And then I subtract all those things, all those entropies for the reactants. So minus the entropy for barium hydroxide in the solid state, because that's how it appears in the reaction. And also minus, I put it in brackets, but you're still subtracting it, right? Minus 2 times the entropy for ammonium chloride in the solid state. And then I just look up these numbers, right? I just look up what the entropy of all these things are, and I just literally just copy them down. And then ran the calculation, I get 359.2 joules per Kelvin mole. So if you did the same thing if the question asked what's the enthalpy, you would do the same thing, only instead of entropy values, you'd put in the enthalpy values, right? And you'll get 51.1 kilojoules per mole. Okay, that's the enthalpy of this particular reaction. So it's positive, so it's endothermic. Okay, and I can also see that the enthalpy of the reaction is positive, which means that the reaction becomes more chaotic as it goes forward, right? Which kind of makes sense. I can sort of guess that just by looking at it, because look what we got on the product or on the reactant side. I've got a solid and I've got 3 solids. So 3 solids on one side, and then I've got a solid, 2 gases, and 2 liquids. So I mean, not only are there more molecules on this side, but most of them are gases and liquids, which have a higher entropy sort of in general. So even without doing this whole calculation, we should have been able to guess that this reaction should have produced positive entropy, because the product side is more entropic, right? There's more of it, and they're in states that are, in general, have higher entropies. So I was expecting a positive number there, and we got a positive number, so good. Okay, so based off of those 2 numbers, is this reaction spontaneous? Well, it depends. It depends what the temperature is, right? So whether or not this reaction happens spontaneously depends on the temperature. And if I want to know what that threshold temperature is, I'll just take the same sort of, I'll use this equation, that the threshold temperature is delta H over delta S. Again, which comes from me just setting delta S of the universe to 0, right? That threshold, that's the minimum, or that's the threshold value where this thing's going to be spontaneous. So I have both of those numbers, and I just throw them in. So delta H is 51.1 kilojoules, so I put that into joules, and then I divide by 359.2 joules per mole Kelvin, and I get the minimum temperature. So yes, this thing is spontaneous if the temperature is higher than 142.3 Kelvin. Then it's going to be spontaneous. Okay. If it's below that, then it's not going to happen spontaneously. All right. So I will leave that there. We still have the Gibbs free energy to talk about, but for now I think that's all I really need to focus on as far as entropy goes. All right, how is that for everyone? Go ahead and keep typing in any questions that you have. I'm gonna start thinking about more logistics, and so think about this as well. Do we want to do this twice a week? So do we want to do this on Mondays at the usual meeting time and Wednesdays at the usual meeting time? I'm game for that. You let me know if it's something you want, and we'll do that. Because we technically have to go. I mean, I know you probably looked at it already, but we could still go through like the Gibbs free energy stuff, because I know there are questions on your assignment that deal with Gibbs. Yeah, so if you want to be able to answer 3C, I mean, you could look through the Gibbs notes yourself, or we could talk about it on Wednesday. So let me sort of gauge the room here. Do we want to do this again on Wednesday? And just sort of have like a regular schedule where we stream Mondays and Wednesday mornings? Twice a week works well. Okay, so I'm seeing... Okay, so I think we will. Okay, we will do that. We will do this twice a week then. Is there anything else that you guys want to cover other than like the lecture stuff? Because we could... What could we do? It's hard doing homework help. Here's what we could do. After we finish with these notes, which won't take long, what we could do, I could try like hooking up my, or like connecting, mirroring my my iPad, and we could just go through the assignment together. That might work. Yeah, I mean, because I don't want to do it for you, but I mean, we'll find a way to make that work so it's not just me giving you the answers. We'll try and make it like interactive somehow. Okay, so Amanda asks, so when we're using the equation for T threshold, you're assuming that, yeah, that's where it comes from, because the condition, remember, is that delta S of the universe is going to be greater than 0 if it's spontaneous. So that's my check. So the calculation we keep doing is seeing whether or not delta S of the universe is greater than 0. If it's not greater than 0, then it's not spontaneous. So we're just choosing like right smack in the middle of less than 0 and greater than 0, which is exactly 0. We're using that to sort of gauge what the temperature's got to be at 0, or like at delta S universe 0, and then we can say, okay, well, any temperature above that is going to be spontaneous. depending on what delta S is, right? If it's positive or negative, but essentially, if it's that gives me sort of like the threshold temperature, and from that, it's one hair above or one hair below, it's going to get me into spontaneous zone. All right. So that's all I got. So what do you guys think? What have you guys been doing with the spare time? If there's a silver lining to all this Corona stuff, it's that I'm able to lecture in my pajamas, so that's nice. Let me see if there's anything else we need to talk about. I don't think there is. I think that was it. If anything else does come up, just let me know. But I think that's it. Oh, the labs. Goodness. We'll talk about the labs on Wednesday, because that's going to be kind of the same thing. But maybe I'll save that for Wednesday. Because I do have your labs from 10.1. I haven't graded them yet, but I'm going to do that soon. The midterm. Yeah, the midterm. I thought the midterm went pretty decent. It's normal, like that kind of midterm is tough. It was a tough midterm. So actually, if you want, we can go through the solutions. Let's do that. Spring. I don't think I posted the solutions, and you already know the solutions to part A. All right, so I'll post this on the Brightspace page as well, if I haven't already. I don't think I have. No. Okay, I'll do that after the stream. Okay, so as far as how it went, I think it went same as usual. I didn't see anything major there. I was a little surprised, like if you weren't able to do like the first question. I was a little surprised at that. There are different numbers, of course, but it's kind of the same procedure as usual. But you know what? Most people got it. So I don't think there's any major issue there. But don't feel bad if you didn't. Like, I know that it's a stressful environment. Oh, by the way, let's address that because the final exam is not going to be quite the same, right? We're not going to be sitting in probably. So I'm planning for a take-home style final exam, which is going to act pretty much like your assignments. So I'll release it, and then you'll have to submit it back into a Dropbox. That's how the final exam is going to go. I think that's the plan. If that changes, I'll let you know. But I'll let you know anyway once we get closer to the date. But that's my plan, is for a take-home final exam. Okay. So as for this midterm, we had a reaction here and some rate data given here, and a possible mechanism. So this type of question was first based on the data, what's the rate law, and then does this mechanism, this proposed mechanism, is that consistent with what the experimental rate law was? So first, we're going to find the experimental rate law just using that data. So the first thing I do is I see that they didn't change the pressure of CHCl3 in experiments 1 and 2. So I use experiments 1 and 2. Okay. So 4 kilopascal, so I'm just taking experiment 2 divided by experiment 1. So this rate divided by that rate equals, these concentrations to some power. I don't know. I can't use 1 and 1 because it didn't say that it was an elementary reaction. So I got to use x and y, or m and n, whatever you use for your variables. So I put those values in, but the hundreds cancel because they're the same. So I can just cross those out, and then I'm left with 400 over 100 to the power of x, which I can sort of condense to 4 to the power of x. This side is 2. So 4 to what power gives me 2? Well, that would be 1/2. So x would be 1/2. Okay. Then I'll pull the same stuff with 3 and 1, with experiments 3 and 1. I don't have to use 3 and 1, but because that might have thrown you for a loop, because there's no, between experiments 3 and 1, no two things are like the same. But it doesn't matter because I already know what x is. So x doesn't have to cancel, right? The x term, the one corresponding to Cl2, doesn't have to be 0, right? Doesn't have to cross out. So I just take 3 divided by 1. So this rate, 5.657 divided by 2, equals the pressures, right? So 200 to the power of what I now know what x is. So 200 to the power of 1/2 times 200 to the power of y divided by 100 to the power of 1/2 times 100 to the power of y. And so the only variable I don't know there is y. So I kind of pull the same stuff. 5.657 divided by 2 is that, 2.8285. 2 to the power of 1/2 is the square root of 2. 200 divided by 100 is 2, all to the power of y. And then I just solve for y. Y ends up being just 1, right? Because 2.8285 divided by root 2 is just 2. So 2 equals 2 to the power of y. Y has to be equal to 1. Okay. So there's that rate law. And then deriving it from the possible mechanism, well, I use the slow step, which is this one. So there's the slow step, right? And so that's what's sort of governing the rate of this reaction. And so I write the rate law according to that step. So I just say rate is equal to K2, because it's the second step. I don't have to call it K2, but I called it K2, times the pressure of Cl times the pressure of CHCl3. Now, each of these steps are elementary reactions, so I don't have to put x and y here. It literally is whatever's in that equation. So that's the slow step. If there are any intermediates in there, I got to take care of them, and there is. There's an intermediate right there. The chlorine does not show up in the overall balance equation, so it is an intermediate. Right? So it's an intermediate, so I substitute it using any of these other equations that have Cl in it. So I could have used this one, although it's probably a lot easier to use this one because this fast equilibrium is sort of governing it's the first line, right? It's the first sort of bottleneck. So that's the one that's probably controlling the concentration of Cl. So I use that, and I say, well, capital K1 is equal to Cl squared over Cl2, right? Products over reactants. And I just rearrange for Cl and plug that into my pressure term here. Okay. So when I did that substitution, I can group my rate constant, so K2 times the square root of K1. I can just call that K, like K prime. And what am I left with in terms of pressures? I'm left with the square root of pressure of Cl2 and the pressure of CHCl3. Okay. So my rate law ends up being K prime times pressure of Cl2 to the power of 1/2 times pressure of Cl or CHCl3, which is exactly consistent with the experimental one. So yes, it's consistent with the rate law. Okay, but sort of common steps, the same steps you would have used for the other, I think, 2 or 3 problems that we did kind of like this. For question 2, we've got the 2 scenes, or the 4 scenes here. The first one's just asking to rank this thing as y goes to 2 z's. Y is red and z is green. So obviously the first one is C because it's nothing but red. And then A has a little bit more green in it. And then B and D have sort of the same number of green to reds. So both B and D are at equilibrium. So it was C, then A, then B is the same as D because they're both at equilibrium. Okay. And the last one, to calculate what K is, the equilibrium constant, I have to use the scenes where there's actually an equilibrium. So either B or D, doesn't matter. And then I look at the concentration of Z, and Z is green. So the number of greens, 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 greens in there. So I say, well, the concentration of Z is going to be 8 times 0.025 over 0.4. Now the 0.025 is because the question states each one of these spheres represents 0.025 moles. And the volume of this container is 0.4 liters. Okay, so that's why I'm using those numbers to calculate the concentration. Okay. Same thing for Y, the number of reds. Well, 1, 2, 3, 4. I count 4 reds. Each of them counts for 0.025 moles, and then we divide by 0.4 liters. Okay. So Kc is just going to be those concentrations divided by themselves. So Z squared, right, because it's from the balanced chemical equation, there's a 2 in front of that Z. So the K is going to be Z squared over Y. And I just put in those numbers, and I end up getting a K value of 1. So there we go. Question 3 was a pH one, using the Henderson-Hasselbalch equation, essentially. So the first one, they actually give you you have a solution of NH4 and NH3. So you have an acid and its conjugate base. Just use Henderson-Hasselbalch. So the pH is equal to pKa plus log of base over acid. The pKa, they don't give you explicitly, but they do give you the Kb. And if you have the Kb, you can sort of work your way to the pKa, right? Take the negative log of it to get the pKb, and then subtract it from 14 to get the pKa. So that got me the pKa. The concentration of NH3 is 0.486, so I put that number right in there. And the concentration of NH4 is not 0.315, it's actually 2 times 0.315, right? Because each one of these produces 2 NH4s. So the concentration of NH4 is actually 0.63. So I put those 2 numbers in, and all I do is I run it through the calculator, and I get a pH of 9.14. So this combination of things would have a pH of about 9.14. Okay. Now the other one, part B, this time it's a reaction because I've got an acid and a base, like a strong base in there. So there's going to be, it's sort of like a titration. So I start with NH4Cl, and I'm going to add some NaOH to it. So this is just an acid-base reaction. On the other side, right, I get the Cl swapping places with the OH, essentially, to give me NaCl plus ammonium hydroxide. But ammonium hydroxide, we've used that in the lab a bunch. That's just the same thing as ammonia, right? It's ammonia and water, but that's how that breaks down. And that's what I'm really focusing on. I'm really focusing on the ammonia and the ammonium, right? The NH4 and the NH3. Because I want to pull the same trick. I want to just use the Henderson-Hansbach equation to put in whatever the ammonia is and put in whatever the concentration of ammonium is, and that should give me the pH. So I'm trying to do the same thing. I'm trying to get the value of NH3. I'm trying to get the value of NH4. Okay. So I start with 0.264 molar of NH4Cl, and I start with 0.196 molar of NaOH. So those are my initial conditions. Don't care about NaCl. I only care about NH3, and I start with essentially none of it to start with. But then according to this balanced chemical equation, you're going to lose X amount of NH4, you're going to lose X amount of NaOH, and you're going to gain X amount of the NH3. Okay? But because this is like a full arrow, the X is basically whatever the limiting reagent is, right? And so because there is less NaOH, I know the NaOH is going to run out first. It's a 1-to-1 ratio. So I know my limiting reagent is the NaOH, and so X has to be 0.196 because the amount of NaOH at the end has got to go to 0. Okay, so that's where that comes from. So I now know what X is. So I just plug those in to my final expressions. So the final amount of NH4 is going to be 0.264 minus X. But I know what X is. It's 0.196. So that leaves me with 0.068 molar of ammonium. And because the ammonia is whatever X is, it's just 0.196. So I now have those two numbers. I have ammonia and I have ammonium. And I literally just put it in the same formula as before. So the pH is equal to the pKa plus the log of ammonia, so NH3, 0.196, divided by the ammonium, which is 0.068. Okay? And I get 9.7 for that one. Stop me if you have any questions. Of course, just bring it up in the chat and I'll address it. But that was how question 3 is done. All right. Question 4 is more of an equilibrium one. Some hydrogen and some iodine are mixed at 229 degrees in a 1 liter container. When equilibrium is established, the following concentrations are present. So this is at equilibrium. HI is 0.49, H2 is 0.08, and I2 is 0.06. And then they say if we add some more HI, what are the concentrations going to be once it reestablishes equilibrium? Well, first thing I can do is I can calculate what Kc is, or what the equilibrium constant is, because I have all the equilibrium concentrations. And the equilibrium constant isn't going to change just because I add more of one thing. So Kc is just going to be the concentration of HI squared, right? Because this is the reaction, this is the balanced chemical reaction. So HI squared over H2 over I2, and I get 50 for a K value. Now, when you add more HI, this side of the equation goes up, which means the equilibrium's got to shift towards the reactants to reestablish the equilibrium, right? And most of you got that. That's great. So I just use, I run it through an ICE table. I put everything in moles here. I didn't have to, I guess, but just sort of habit, because they said they added 0.3 moles. But since the container is 1 liter, moles is going to be the same thing as molarity. But in either way, I took all those concentrations, multiplied them by 1 to get the number of moles, and then I added 0.3 to the HI. So that was the initial amount. And because of that excess of HI, it shifts towards the reactants. And so I'm going to lose 2 equivalents of HI, and I'm going to gain an equivalent of I2, I'm going to gain an equivalent of H2. So then at equilibrium, these are my expressions, right? Initial plus final, or sorry, initial plus change, and initial plus change. So that's what it's going to look like at equilibrium. So putting that into my equilibrium expression, again, I already know what the equilibrium constant is. It's 50. And then I say equals 0.79 minus 2x squared. Again, I'm following the same procedure here. Right? That, whatever that is at equilibrium, squared. Okay, divided by the reactants. And then all I do is I solve this thing for x. It's going to be a quadratic, right, because it's 2x squared. You might get away with, you could probably get away, especially with the top one, with saying, maybe x doesn't matter all that much, because it actually is quite small compared to x. I don't think it's small enough, to be honest, and I wouldn't have done that anyway. I wouldn't have think to do that, because the equilibrium constant is kind of big. So because the equilibrium constant is kind of big, I don't think it was a good idea to just drop x. I usually drop x whenever like the equilibrium constant is quite small, like really, really small. But it wasn't in this case, so I left it in. So I ended up having to solve a quadratic, which again, I just went on math.com and solved that quadratic. And once I knew what x was, I put that x value back into here and divided it by 1 liter, right, to get the concentrations of each of these. So the concentration of H2 is going to be 0.08 moles plus the x value that I just found, 0.0329, divided by 1, which got me 0.113 mole, 1.113 molar. And I did the same thing for I2 and HI to get those concentrations. There we go. Are there any questions on that? Because if not, I think we'll leave it there, and then we'll pick up the thermo stuff, the rest of the thermo stuff, and talk about the assignment on Wednesday morning. I'll stick around for another minute or so if you have any, or I'll stick around for as long as there are viewers. If you have other questions, just drop them in the chat. Otherwise, let's call it here, and I'll see you again on Wednesday. Yeah, so I'm getting emails from you that you can actually see the chat, but when I go on YouTube and I click on the link, I don't see it at all. So yeah, like it doesn't show up in the box like below my webcam where it's supposed to, which is weird. Okay, I'm not seeing anything happening in the chat. I'll just give it another minute or so just to make sure, but otherwise I think I'm going to close it in a minute. All right, seeing nothing. So if you do have any concerns or questions, just send them in an email and I'll address them there. All right, see you everyone. Maybe if I know how to even turn this off.